So we'll have two talks, and then we finish up with the discussion on the subject. And the first also will be by Michael from the University of Swansea. I just hand over to you.
Cool. Hello. Is everybody okay? Are you still happy? Yay. So this might be kind of a bit redundant, because I think I spoke to a lot of you during the poster presentation. But what I'll try and go through is a bit of our work using graph CNNs for, admittedly here we say medical images, but actually more kind of slightly more efficient 3D segmentation. And I'll also touch on the idea of graph CNNs as an introductory, because it's quite a novel field, and I really believe that it does have quite a nice purpose and sitting within the community itself. And what's quite nice is it does tie in with a lot of the talks that we've actually had so far as well, so I can use those for my own nefarious benefits. So I'll be talking about representation learning in general, and this will be pretty redundant for a lot of you here, but it is important to kind of set the scene for where we then go in terms of graph CNNs. And then we will look at this idea of learning or representation learning in irregular domains, and then we will look at the idea of using this in a multi-resolution scenario, and I'll explain why we've kind of gone down this route. And then I'll look at what's actually in the paper is a case study of using this for medical segmentation, hence the title. Okay. So we're all familiar with deep learning so far, and it's this idea of learning this representation from very low-level features, if possible, and it gets pretty good performances in what is the majority of all of our fields. This kind of image-based problem, 2D grids, 3D volumes, things like this, right? Does well for a numerous number of tasks, recognition, detection, style transfer, all of these things, right? And it does show strong accuracy in numerous data sets as well, which we've touched on in the talk so far. We do know that we need large amounts of data, and we do need some kind of ability to look at the hyperparameters in terms of architecture design, and there's methods that go through trying to refine that approach. But it seems like a really useful kind of field within machine learning at the moment. Right? And that's given birth to essentially a plethora of different kind of implementations of various constraints for use during deep learning. Autoencoders, multi-layer perceptrons, CNNs, all of these things. Right? And at the moment, the way that I've been kind of using this graph CNN approach is along this kind of narrative going from neural networks to CNNs to graph CNNs. Okay? So we have this ability to learn a representation, and in neural networks we're not implying any kind of spatial information between those inputs. Right? They can just be generic features. How much hair does this animal have? Does it bark? Does it meow? Things like that. Right? And we then moved on to applying more and more constraints in order to kind of adapt these to different approaches or purposes. Okay, but if we look at a neural network and its lack of spatial information, we can then move on to what we've kind of adopted as a community and really made strong usage of is the idea of a CNN and the ability to learn localized information which translates across an input domain. Right? And we see strong responses and performances in various data sets. Right? So MNIST nowadays gets just thrown around as a baseline, but we are doing really well. And that's all because of essentially two main contributing operators, right? This idea of a convolutional operator and a pooling operator. Okay? So given a kind of localized receptive field that's learned, or has a learned weighting associated with it, right? And we convolve that across, we get some feature map out which is responding to that at a local scale. Right? And then at pooling level, taking some input map and generalizing that down, not only to increase that generalized format, but also save some space. Right? But not every problem, unfortunately, is a regular 2D, 3D, ND grid. Yeah? So we have meshes or point clouds, right? We have the Minnesota road network, we have the human skeleton that we've seen in previous talks, right? They do have localized information. If I move this hand, right, I expect this hand and this elbow to be more correlated than what my foot is doing right now when I'm performing the action of wave, right? If I see a pileup of traffic in the center here, I expect this to be more related in these roads than on the roads in the outskirts of the city. So there is localized information that we'd like to understand, but we can't necessarily make use of a CNN to learn these. Okay? So how do we get around that issue? Well, I've seen papers just straight up brute force a domain into an image, take a mesh, voxelize it, take a time series of data and just stack the rows to make an image and pass a CNN over it. I've used the CNN for X, Y, Z. My paper gets published, hurrah. Right? Perfectly fine. Except for the fact that it's failing that assumption, that core assumption of a CNN, which is this idea of this grid-based input, this array-based input. So if we represent our domain as a graph, right, where we have edges and nodes on those graphs, rather, that represent sample points in that domain, and we have edges on those relating nodes together, right? So an edge-weighted graph, saying that the shoulder is more related to the elbow. There is no connectivity between my hand and my leg, or something like this, right? And then I can use graph-based signal processing techniques to essentially learn weights on, or couple that with an optimization scheme like in deep learning, to learn weights, filtering operations which are localized on that graph. Okay? So we have a graph representation of our domain, and along with that we have the usual kind of culprits, this weight matrix, determining how related given nodes are, whether they're associated together based on the adjacency matrix, and we can essentially then represent the entire graph structure as this Laplacian out. And then if we want to, we can think about how do we get a convolutional operator that resides on this graph. Okay? There's a couple of approaches to this, but I'll talk about the one that my research tends to focus on at the moment, which is this idea of this spectral representation of the frequencies of the graph. Right? So you have this graph Fourier transform, and we're able to go from a graph signal in its original spatial domain, so this, what looks like an image, but is really just a 2D grid graph, right? With signals that reside on it, so the Pepper's image, and we're able to essentially do the graph Fourier transform using the eigenvalues and the eigenvectors of that Laplacian, that graph Laplacian, to convert it into a frequency spectral signal. Okay. And then based on signal processing techniques, we can then utilize the spectral form of a convolution. Okay. So we just have the ability to now change from our spatial domain information via essentially a matrix multiplication to the frequency domain and back again. Okay. And these eigenvectors show nice kind of structures within our data. So if we have the human skeletal graph, we can see frequencies related to the overall body, arms, legs, the left side of the body, the right side of the body, all of these things. Okay. And then we have the ability to essentially do a filtering operation in the spectral domain. Right? So like we've seen before, we have the graph Fourier transform on our data, and then we essentially weight that spectral information. So we weight the frequencies via a learned weighting system, and then inverse graph Fourier transform that back. Okay? Now if we couple that with deep learning, we can say that we want to learn or optimize over this W based on our data set. Okay? We have analogous pooling operator. Okay? So we want to essentially do graph coarsening in some way. We want to be able to contract nodes or reduce nodes or remove nodes, but still generalize that information and store the space, save space in terms of the information that we're carrying. So we might have, again, the graph of the 2D grid with a signal that resides on it, okay? And we're able to graph pool or graph coarsen this grid down. And what's nice with some strategies is, analogous to how we have up-pooling and upsampling, we are able to recover that signal as well with some loss, but fine. Okay. So we have our two main components now of what we've been used to in a CNN, right? But now we're not stuck with a 2D grid, 3D grid, n-dimensional grid or anything like this. Now we can say, actually, we want to learn how localized features interact on the human skeleton, on a point cloud, anything like this. Okay? And obviously this has lots of different applications, right? So the piece of work that I'm going to talk about in a minute, right, this idea of multiple scales or multiple resolutions as a sampling operator inside the same batch, something that you wouldn't be able to convolve a CNN over without a large amount of complexity before, right? But now we have it in the same operation, right? Maybe face segmentation or voxel kind of segmentation of meshes, human skeleton, all these things. So the one thing that I saw when I was reading the literature in terms of these 3D segmentation approaches, when it came to deep learning, like Andrew said, it's kind of expensive when you go to very, very large volumes and you want to go through the entire thing. Okay. Now, my problem wasn't explicitly a segmentation of the entire volume, but I wanted to still detect a very small structure within there. Okay. So it was expensive for me to go through everything. And I was thinking to myself, well, what information would I, try to use to make sense of the volume as a whole in terms of where the object is within that volume, what position it is, what orientation, and things like that. And that obviously led to region proposal networks and things like this, where maybe you have two different approaches. You could have multiple scaled branches going into and then embedding different scaled information together, and then concatenating that, and then having another neural network kind of branch afterwards doing the actual main driving work. But then you have three branches in the same network, so it's higher complexity. There's no guarantee that features learned at this kind of high resolution are the same as at the lower resolution, or are related to the lower resolution. Or we could go for the more common now dilated kernel kind of approach, where maybe we say we want to learn the same feature but at different scales. So if I have a diagonal kind of edge, it doesn't matter whether that's on a small scale or a large scale, it's still a diagonal edge to me, right? But that doesn't necessarily correlate with what I wanted to learn, which was contextual information. Where does the object of interest reside within the entire volume, and are there any cues contextually around that tell me where it should be? Okay? So the idea was to couple local and contextual information for the same sampling operator, and use that to feed into a neural network or a graph, convolutional neural network, so that we can learn localized features. Okay. So I have a sampling operator, which is essentially this, right? A dense core, which is high resolution, so really fine-grained local information, and then successive kind of layers of lower and lower information, contextual information at a wider a wider scale of interest. Okay? And I want to feed that into my graph convolutional neural network for essentially one purpose within this entire segmentation pipeline, and that's to get a pose estimation for an initial shape model to then feed into the segmenter. So all of this method was a novel proposal. I talk lightly about this because I prefer this side of my work. But this idea of using this multi-resolution sampling operation to get a feel for what position, what's around my object of interest, and what orientation is it in as well. So can I use the bones in the chest as a kind of guide as to where I should be looking? It's pointless me looking over here for my heart valve if I can see that my neck tissue is over here at a low resolution. Okay. So I have the ability to, or I've produced the multi-resolution sampling operator, right, and it's just a slice through in 2D. But essentially, if we look at the original image at high resolution, right, and now I have this multi-resolution sampling operator where the core is very, very high-resolution information, right? But actually, the external, I only have about 18 or so pieces of data there, instead of the entire 512 voxel sample. Okay. So I'm able to sample in on a place of interest, feed that into my graph CNN, and train it to get a prediction of position. I train it for position, and that reduces my space down in terms of where I'm looking within my entire volume, right? The entire, torso of the human. And then I'll train one to identify and detect position and orientation, and then I can reduce that search space down as well. Okay. So I feed that back into the pipeline. And then we do some kind of iterative deformable segmentation to search for the refined boundary, essentially. Trying to localize the boundary for the shape of interest. That's good. And we get pretty decent results. Okay, so because of the marginal space learning kind of graph CNN implementation portion of that pipeline, I'm able to localize really closely into both the true position of the heart valve and its true orientation, right? And using that as a set of pose parameters to initialize my shape model, that then allows me to segment quite nicely as well. So because I'm able to really localize in on where it should be, that kind of iterative deformation of my statistical shape model allows me to get quite close to the ground truth boundary itself. Okay. And fine, because everyone likes a table, like I said, and improved on the state of that as well. But also did well compared to methods that do not take localized information into account. So this improvement over a neural network on the scene. Cool. Nimesh?
Hello. Have you considered incorporating wavelengths as a method of achieving your multi-resolution?